In this example, we want to go over how to evaluate the RRAM of a function and how to use it to evaluate the definite integral. So here we're given the function f of x equals x squared plus x plus 1 for x between 0 and 3, and we want to evaluate the RRAM of f, and then we want to evaluate the definite integral from 0 to 3 of our function by evaluating the limit as n goes to infinity of the RRAM. By definition, this quantity right here will be our definite integral from 0 to 3. So we start out with our definition for RRAM. Remember, it's equal to this, where in this case the a is equal to 0 and the b will be equal to our right-hand endpoint, which is 3. So putting 0 in for a and 3 in for b, we end up with this. And now what we have to do is simplify this expression by putting I times 3 over n in for all the x's up here in our function. And then we'll expand everything and simplify. So evaluating this, we get so now we evaluated the function f of I times 3 over n, and it's this piece right here. Now we will distribute the 3 over n inside, and also we will write I times 3 over n squared as I squared times 9 over n squared. And so what we get then is, further simplifying this, we get so there we just distributed the 3 over n inside. Notice 3 over n squared is 9 over n squared times 3 over n gives us the 27 over n cubed. And then 3 over n times 3 over n gives us 9 over n squared, and 3 over n times 1 is the 3 over n term. Now we will distribute the summation into this term and this term and this term, and what we get is so we distributed the summation, and at the same time notice that we pulled out the constant terms outside of the summation. So we pulled this one outside of the sum here because it doesn't depend on I. We pulled the 9 over n squared outside of the summation as well, and then we pulled the 3 over n out, leaving a 1 outside of its summation. And now what we'll do is we'll use our summation formulas for this term and this term. And this term right here is just n. And so plugging in our formulas, what we get is and so here we go. Now this is our RRAM. So this is what we wanted to find. So this is what we wanted to find here. We can do a little simplification with this. Notice we can cancel these ends here, so we just have a 3 out here. And so this is our answer. Now let's evaluate the limit as n goes to infinity of the RRAM and see what we get for our definite integral. And so evaluating the limit, now if we look down here, notice something about this. This term right here in the numerator, the highest power of n is going to be 2n cubed. And so if we're looking at the limit as n goes to infinity, the degree of the top is going to be 2n cubed, and the degree of the bottom is also n cubed. So our limit as n goes to infinity is going to be 2 over 1, and then we have the 27 and 6. So this term right here in the limit is going to contribute this. So we get 27 over 6, 27 over 6, and then the quotient of the leading coefficients, 2 and 1. Now the next term, notice this one right here. This has a leading coefficient of n squared, or a leading power of n squared and a leading coefficient of 1. So looking at 1 times n squared over n squared as n goes to infinity, this limit is going to be 1, and then we have a 9 over 2, so we get 9 over 2 times 1, and then finally we have the 3 left over right here. And then simplifying this, we get, and finding a common denominator, and then just adding everything up, we're going to get 99 over 6, or 33 halves. And that is 16.5. So that's our limit as n goes to infinity of the RRAM, and that is what this is equal to. So our definite integral we have found is equal to 16.5, or 33 halves. And so that concludes this example of finding the RRAM for a function and using it to evaluate the definite integral by taking the limit as n goes to infinity of the RRAM.